In 2022, physicists in Delft teleported information across 3 quantum nodes, and not a single particle actually moved. By the end of this video, you'll understand exactly how quantum teleportation works, why it doesn't break the speed of light, and how Beijing, Chicago, and 27 European nations are racing to build the first unhackable internet using this technology. Let's get something out of the way immediately. Quantum teleportation has nothing to do with Star Trek. You're not beaming atoms from one place to another. You're not disintegrating matter and reconstructing it somewhere else. What you're doing is something arguably stranger. You're destroying information in one location and having it appear perfectly, instantly, in another location. The particle that held that information, it never moved. It never had to. Right now, you're watching this video because billions of photons carried data through cables and routers to reach your screen. Classical internet. Bits, ones and zeros copied and amplified millions of times along the way. But here's the problem. Every time you copy data, you create opportunities for someone to intercept it. Every router, every amplifier, every junction is a potential vulnerability. The quantum internet promises something different. Communication that is physically impossible to eavesdrop on without detection. Not difficult, not encrypted, physically impossible. And the foundation of this unhackable network? Teleportation. But wait, if teleportation doesn't move particles, what exactly is being teleported? The answer is quantum states. And to understand that, we need to talk about the weirdest phenomenon in physics: entanglement. In 1935, Einstein called this spooky action at a distance because he thought it was so absurd it must be wrong. But he was wrong. Entanglement is real, and here's how it works. When two particles become entangled, their quantum states become linked. Measure one particle, and you instantly know something about the other, no matter how far apart they are. In 2017, China's Michia satellite demonstrated this across 7,600 kilometers between Vienna and Beijing. Measure a photon in Austria, and its entangled partner in China correlates instantly. But here's what trips people up. This isn't communication. You can't use entanglement alone to send a message faster than light. The correlations are random. There's no control. So how do you actually teleport information? You need 3 things. This is the Bennett protocol from 1993, and it's beautifully counterintuitive. First, Alice and Bob share an entangled pair. Alice has particle A. Bob has particle B. They're entangled. Second, Alice has a third particle, call it particle X, whose quantum state she wants to teleport to Bob. Third, Alice performs something called a Bell state measurement on particles A and X together. Here's where magic happens. When Alice measures A and X together, she destroys the quantum state of X, gone. But the measurement produces 2 classical bits of information, regular ones and zeros, that describe the result. Alice sends those 2 classical bits to Bob through a normal channel. Phone call, email, carrier pigeon, doesn't matter. Bob receives those bits and performs a specific operation on his entangled particle B. The operation depends on which bits Alice sent. And here's the punchline. After Bob's operation, particle B now has the exact quantum state that particle X had before Alice destroyed it. The information teleported. No particle moved. Nothing traveled faster than light, because Alice still had to send those classical bits, which travel at normal speed. So that's the theory. But is anyone actually doing this? Yes. And the networks are bigger than you might think. In 2020, the Chicago Quantum Exchange demonstrated quantum teleportation across 44 kilometers of existing fiber optic cable connecting Argonne National Laboratory, Fermilab, and Northwestern University. Fidelity, over 90%. That means the received quantum state matched the original 9 times out of 10. But Chicago's network is modest compared to China's ambitions. The Beijing-Shanghai quantum backbone, completed in 2017, spans 2,000 kilometers. That's roughly the distance from New York to Denver. It uses 32 relay nodes and represents the world's longest quantum-secured communication line. Now here's where quantum networks get fundamentally different from classical ones. Your home router copies signals constantly. Data comes in, gets amplified, gets copied, gets sent along. No problem. Quantum routers cannot do this. In 1982, physicists Wouters and Zurek proved the no-cloning theorem. It is physically impossible to create an exact copy of an unknown quantum state. You can't amplify quantum information. You can't back it up. You can only teleport it, destroying the original in the process. This creates an enormous engineering challenge. Photons in fiber optic cable lose energy, about 0.2 decibels per kilometer. Run the math, and after 100 kilometers, only about 1% of your photons survive. After 200 kilometers? Basically none. Classical networks solve this with amplifiers. But you can't amplify quantum states. The solution is quantum repeaters. Instead of amplifying signals, you break the journey into shorter hops and use entanglement swapping to extend the quantum connection across each segment. But here's the reality check. Fully functional quantum repeaters don't exist yet. They're experimental. The technology works in labs, but deploying them at scale remains one of the biggest unsolved challenges in quantum networking. Which brings us to Europe's bet. EuroQCI, the European Quantum Communication Infrastructure, is the most ambitious quantum network project currently planned. The goal: deploy quantum communication across all 27 EU member states by 2027. The approach: hybrid. Fiber optics for ground connections. Satellites for long-distance links where fiber losses would be too severe. And in May 2022, researchers at Tech in the Netherlands achieved something that had never been done before. They teleported quantum information between non-neighboring nodes in a 3-node network. Alice teleported to Charlie through Bob, without Alice and Charlie ever sharing direct entanglement. This might sound incremental. It's not. This is the first demonstration that quantum networks can route information like classical networks do, not just point-to-point, but through intermediate nodes. So why does any of this matter to you? Quantum key distribution, QKD. With quantum networks, two parties can share encryption keys that are guaranteed secure by physics. If anyone intercepts the quantum transmission, the act of measuring disturbs the quantum states. The eavesdropping is detectable. Always. No algorithm to crack. No computational power that breaks it. The security is baked into the laws of the universe. Here's where we are right now. 2017. China completed the Beijing-Shanghai backbone. Same year, intercontinental quantum communication via satellite. 2020. Chicago demonstrated metropolitan-scale quantum teleportation over existing fiber. 2022. Delft achieved multi-node routing. 2027. Europe plans continent-wide quantum infrastructure. The quantum internet isn't science fiction. It's infrastructure being built right now. Quantum teleportation doesn't break physics. It exploits physics. Entanglement, superposition, and the no-cloning theorem combine into something that sounds impossible but works. Information moves without particles moving. Security comes from measurement disturbing states. Copying is forbidden by universal law. The first quantum internet nodes are already operational. The race now is scaling them, building repeaters that work, satellites that distribute entanglement globally, and networks that connect not just labs but cities and continents. If this made quantum mechanics feel slightly less like magic, hit subscribe. Next video, we're going deeper. Quantum computers aren't just faster. They solve problems classical computers literally cannot touch, even with infinite time. I'll show you exactly why. See you there.